way of improving the quality of the recording because what I saw was actually pretty bad. So, like, can I tell the PC that it's supposed to, I mean, it's recording from my source, right? So, if it is recording at my source, then it should be good quality, but very, very bad quality. Something like 480p or something. So, do let me know if there is a way of making these neat recordings better. It's for everyone's good. Anyway, so let me know if you're able to see my screen.
Yes, sir, your screen is visible.
All right. So last class we saw that you need two independent properties to specify the state of a pure substance, simple compressible substance. But in this case, it is true for a pure substance. Meaning, if you look at the state of a substance in the PV diagram, you have this dome where this part of the dome is saturated, is subcooled liquid, is saturated liquid. Then this part of the dome is saturated vapor. Okay, so in this particular case, how do the isotherms look like? The isotherms will look like something like this. And after a certain point, which is the critical point, this is how the isotherm varies. All right. So similarly, for so in order to specify the state, so suppose I want to specify this state, I must specify P and V or P and T or T and V and so on. Okay. I mean, till now, this is what you have learned. You have to specify two independent parameters. But here is the important part, and I will keep reiterating this throughout the course. When the liquid reaches saturation, this particular temperature is not independent of the pressure. So at this particular pressure, this is the temperature which is fixed and it is like the boiling point. Okay. So the T saturation is dependent on pressure, and as a consequence, T is dependent on P. We cannot find out a state if we specify pressure and temperature simultaneously. So over here, in order to specify the state, we must specify the quality. So this particular point over here has a quality of 0, whereas this particular point over here has a quality of 1. And in the previous class, we had briefly seen an example of this. So far, you have learned about PV diagrams and TV diagrams. So once again, TV diagram also looks quite similar, but how do the isobars look like? Let me draw it in a different color. The isobars will look something like this. Okay, this is how the isobars will look like. Oops. Once again, if you look at these points, they are called as superheated vapor. If you look at this point, they are subcooled liquids. This boundary is for saturated liquid. This boundary is for rather saturated vapor, and this is for saturated liquid. And the same chain of logic holds true over here as well. And I will just recall once again that if if the quality, if someone says that under saturation at some temperature, say T equal to whatever, you say that the quality is 0.5. If the quality is 0.5, how do you find the specific volume? The specific volume for this would be the specific volume of the fluid plus X times VFG, where VFG is VG minus VL. Okay, and this is tabulated, this is tabulated. So, what can we conclude? That in the saturated region, pressure or temperature can be specified, and the other parameter that can be specified is either the quality or the specific volume. Because once you specify the specific volume, you know what temperature or pressure is, so you will know what the specific volume of the liquid will be and the specific volume of gas will be. So if you know what the specific volume of the substance is, then you can figure out what X is going to be. Conversely, if someone tells you that the quality is such and such, then also you can use the fact that you know what the temperature or pressure is going to be. You will know what the specific volume of the liquid is going to be, and you will know what VFG is going to be. So if the quality is known, then V can be found out. So V can be found out with the quality and pressure or temperature, or conversely the quality can be found out with specific volume, pressure or temperature. Okay, so far so good, everyone?
Sir,
Any doubt?
hello, sir.
Yes.
Sir, I think you wrote VL instead of VF.
Oh, sorry. Yes, you are correct. Should be F. That's right.
Yes, sir.
Yeah, it's just fluid, liquid. I mean, whatever you want to. Vapor, gas is one thing, and fluid, liquid is the other thing. Good. Thanks for the observation. Okay, so let's do some problems now. So pay close attention. I mean, this is what you signed up for. Okay, some examples. We will do it both with the help of the uh, computerized uh, assistance and with the help of the tables at the end of the book. All right. So the question is, this is an example. So it's simply example 3.1. So the question is as follows. Determine the phase for water and show position on PT. I mean, forget PT. PT is not so important. So we must show the point on the PV diagram and the TV diagram. So the first point that has been given is 120 degrees Celsius and 500 kilopascal. So the question is, what is the phase of the water given this state? So I will tell you how to go about this. So first, let us first draw the PV diagram. So first things first, it is always good to draw a PV diagram. It helps you get an idea of how the curves will look like. So let me draw it in pink. So this is the PV curve. Uh, this is P, this is V, and this is the curve. And how does the isotherm look like? An isotherm will look something like this. Okay, so this is how an isotherm will look like. So this is some temperature, so T equal to constant basically. So it says what is the phase of water for this condition. So in the PV diagram, I will find out the y coordinate where the pressure is going to be 500 kilopascal. So suppose this is the point where the pressure is 500 kilopascal. So my next task, given that this is 500 kilopascal, my next task should be to find out whether, rather, what the task should be to find out what this saturation temperature is going to be. My task should be to find out what the saturation temperature is going to be. Now, if this particular temperature, of 120 degrees Celsius, if it is higher than the saturation temperature or whether it is lower than the saturation temperature, that will decide exactly where I am. Okay. So at 500 kilopascal, I do not know exactly where I will be. So this isotherm could be 80 degrees Celsius. So at 500 degrees Celsius, where will be the 120 degree isotherm? Let me just draw. So if this is 80 degrees Celsius, at a higher temperature, this will be the isotherm. So suppose this is the 120 degrees Celsius isotherm. So at 500 kilopascal, if I drop a horizontal line, this intersection would be the point where the pressure is 500 kilopascal and the temperature is 120 degrees Celsius. Is the logic clear? How to figure out where the point is going to be? This is just a
Yes.
hypothetical situation. I don't know exactly where the point is. Huh? I'm just telling you the logic, how to go about it. Yeah, someone wanted to say something?
No, sir, understood, sir.
Yeah. So, does anyone have any doubt? Anyone, absolutely anyone. On the contrary, so if this were to be, say, let me again draw a new diagram. So say this is 160 degrees Celsius. Oh, not. So this is pressure, this is volume, and this is the 500 kilopascal line. So the horizontal line extending throughout will be the line which is at a pressure of 500 kilopascal. Now suppose this isotherm, so suppose this particular temperature is 160 degrees Celsius, right? So what does that mean? If this is at 160 degrees Celsius, I must go to a lower isotherm. So a lower isotherm would be something like this. So what does this mean? Suppose this lower isotherm I have drawn for 120 degrees Celsius. So where is the point going to lie? It is going to lie between the intersection of this 500 kilopascal intercept, meaning this horizontal line of 500 kilopascal, when it will intersect the isotherm of 120 degrees Celsius. So meaning this is the point where we will have 500 kilopascal and 120 degrees Celsius. So we've discussed two cases. One where the point under consideration is a superheated vapor. Okay, this is an American spelling. Okay, yeah. So we have considered the case where the liquid could be a subcooled liquid, correct? And the third case is when exactly we are sitting on the isotherm. Okay? The third case is as follows. Third case is very simple, that but we then cannot determine exactly where the point is. It is impossible to determine where the point is simply because, so I've drawn the curve again. Now look, if this is the PV diagram and if this is the isotherm, if it so happens that this is the 120 degree Celsius isotherm and this is the 500 kilopascal horizontal line, then what does it mean? There are infinitely many points. There are infinitely many points where you will have 500 kilopascal and 120 degrees Celsius. And therefore, to completely specify where the point is exactly going to lie, I must then specify either the specific volume or the quality of the pure substance. Is this clear? Is this discussion clear? Infinitely many points. So we cannot use temperature and pressure to specify state. Is it okay? Whatever I've just said so far, is this fine?
Yes, sir.
Someone has written to me something in chat. Is it?
Now, can we say here it will be in all three forms?
Where?
Sir, at 120 degrees Celsius,
Hmm.
500 kilopascal pressure, here it will be all three forms.
No,
All
here it cannot be three forms. If it is lying in this dome, then we can say that part of it is vapor, part of it is liquid. Three forms will be in triple point only. We've discussed this in the previous class. Right?
okay.
All right, so now let us actually go into the values. I've shown you the schematic. So see, you must understand how to draw the schematics. Not very difficult, it's a matter of experience. So the question says at 120 degrees Celsius and 500 kilopascal. All right. So first things first, I will refer back to this diagram, to the PV diagram. So what do we need? We need to know what the saturation temperature is. We need to know what the saturation temperature is corresponding to a pressure of 500 kilopascal. Because we want to know Tsat at 500 kilopascal pressure. So let's see. Let me share my entire screen. Is the screen visible?
Yes, sir.
Yes, sir.
All right, excellent. So we have now the saturated water table in front of us. But what are we doing? I mean, we're looking at determining what the saturation temperature is at 500 kilopascal. Okay. So in the saturated water, I will go to the pressure entries. I will not look into the temperature entries, but rather I will look at the saturated water pressure entry. Is this visible to everyone?
Yes,
I
sir.
will look at saturated water pressure entry and I will go to 500 kilopascal in this pressure thing. So at 500 kilopascal, so look, this is kilopascal. At 500 kilopascal, the temperature is 151.86. So let us write it down. So Tsat at 500 kilopascal is 151.86 degrees Celsius. So what does it mean? I will draw it again just for everyone's benefit. I will again draw it. So let me draw this. Now we have one. Oops. So this isotherm is 151.86 degrees Celsius. And this is 500 kilopascal. This is P and this is V. So now we are bothered with 120 degrees Celsius. We would like to determine the state point when the temperature is 120 degrees Celsius. So let us draw the 120 degrees Celsius isotherm. So obviously this is going to be the 120 degrees Celsius isotherm. I mean, we don't know exactly where it is, but qualitatively speaking, this is going to be the 120 degrees Celsius isotherm. This was the 151.86 degrees Celsius isotherm. Meaning the intersection of the horizontal line at 500 kilopascal. So this entire line is 500 kilopascal. And the intersection of the 120 degrees Celsius isotherm with the 500 kilopascal line gives us this point. And this is going to be the point, the state of water at 120 degrees Celsius and 500 kilopascal. And so what is the phase? It's gonna be subcooled liquid. Is this okay? Whatever I have said so far. Now we will do the the inverse calculation. Yeah. Anyone?
So to find the saturation temperature, can we also look at the rather than the saturated liquid table, can we look at the steam table also?
The steam table is the ensemble of all the tables. Steam table, there is nothing like a steam table. It's the collection of all these tables which is known as steam table. This is a part of the steam table.
Oh, okay, sir.
Now look, we're gonna do the inverse, not the inverse calculation, but the other calculation. So we are bothered with 120 degrees Celsius and 150 kilopascal. All right, so now we've looked at already how the PV diagram looks like. Now we will look at how the TV diagram looks. Let's draw the TV diagram. In the TV diagram, we will have the isobars. Okay, let's only draw one isobar. So now you should be able to figure out how to go about doing this. So this is the TV diagram. So in the TV diagram, I have an estimate of, not the estimate, I have exactly the value I need. So let me just draw that this horizontal line, this particular horizontal line is going to be 120 degrees Celsius. Because on the y-axis, I now have temperature, so I cannot work with pressure directly. And so first things first, I must find out what is the value of the isobar. In order to find out the value of the isobar, so this is the entire isobar. This is the entire isobar. So I must know what the pressure, saturation pressure at T equal to 120 degrees Celsius is. So let me go ahead and find out what the saturation pressure at, so P sat at T equal to 120 degrees Celsius for steam. So now which entry should I look at? I have saturated water pressure entry, but I will again go to saturated water temperature entry. So these are the temperature entries. Okay, saturated water temperature entries, and the temperature under consideration is 120 degrees Celsius. So I will go to 120 degrees Celsius. The corresponding pressure turns out to be 198.5 degrees Celsius. Okay, this is the pressure. So at 120 degrees Celsius, it's 198.5 kilopascal. This pressure is going to be 198.5 kilopascal. But we are bothered with 150 kilopascal. So what should I do? Where should I draw the point?
It will be below this isobar.
Why have I written here 150 kilopascal? It's supposed to be 500 kilopascal, right? Weird. The question was 500 kilopascal. The question was 500 kilopascal. Okay. I don't know why I wrote 150. So 500 kilopascal will be somewhere way above this. Like somewhere like this. Maybe not that above. So schematically speaking, this will be the 500 kilopascal isobar. So the intersection of the horizontal line at 120 degrees Celsius and the isobar of 500 kilopascal is going to be somewhere over here. And this point is obviously subcooled liquid. Okay. Is it clear how to do this?
Yes,
Now
sir.
let me go to ES. Okay, and I don't care about saving this file. I'm using the free version, which you will also be using. Let me just increase the font size. New file, new. Then I will go and say that T1. So I will declare them as arrays. Anytime you would like to plot stuff, you should declare them as arrays. So T1 is 120 degrees Celsius. P1 is 500 kilopascal. Okay. So look, I mean, why am I able to write this with confidence? Because it's SI units and the pressure is kilopascal. The pressure is in kilopascal, temperature is in Celsius. So you should remember the energy units are kilojoule. Okay. So I can write them like this. So then I say V1 is equal to volume of water at T equal to T1 and at P equal to T1. Then I simply solve this. So I get a volume of 0.00106. So if you look at the specific volume, the inverse of it does seem like something in the range of 1000. So it's like subcooled water. So let us go to plot. We will do the property plot. In the property plot, we will first choose the liquid. So we will say steam, and then we will choose the TV diagram. Then we will not include any of the constant quality lines, isentropic lines, nothing. We just want pressure of 500 kilopascal. Okay. So let's click on OK. So this is the 500 kilopascal line. Now I would like to overlay the plot with this. I would like to overlay with this T and V. I will go to plot. I will go to overlay plot. Then on the x-axis, I will plot the array points Vi. On the y-axis, I will point the array points Ti. And I will make it magenta. Say OK. So here is the point. Okay, here is the point. I'm not sure if you're able to see that, but it's subcooled. It's very close to the saturated liquid line. Can you see it? And it's below this. So that was what our conclusion was. It should be below the curve, the 500 kilopascal curve. So this is the 500 kilopascal isobar, and the point is over here. 500 kilopascal isobar. The point is over here. Okay. Do you see how you can do it
Yes.
on a computer? Now you may think that okay, that's fine, but how do I find out this P saturation at 120 degrees Celsius? Suppose I want to find out. So I say P sat equal to pressure of water at T equal to T1 and X equal to 0. This will give me the saturation pressure. So P sat is 198.7 and it was 198.5. I mean, the small differences are because the computerized tables are using higher order interpolations inside internally, so they give you better values. All right, is this clear? Now, what do you think will happen if I choose any other value of x I am fetching the pressure of water at a certain temperature at some x. Now, this x could be anything. Even if I say x equal to 0.5, it will still return me the same value, 198.7. Even if I make it x equal to 1, it will give me the same value, 198.7. Essentially, what we are doing is, and I'm repeating this once again, I am asking the computer to give me the pressure at this point, 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 this point, this point, anywhere inside this saturated liquid, saturated dome, anywhere inside this dome, all the points will have the same pressure and the same temperature. That is why they are not independent. Okay, is it fine? If I were to query the specific volume, then yes, I would get different values every time. If I say V inside, and I say volume of water, so let's see. Now this is the specific volume of water at x equal to 1. Say if I do 0.5, obviously it changes. See, it has gone from 0.8 something to 0.4 something. If I make it 0.2, it will become 0.1791. So basically at along all these points, pressure and temperature will remain the same. Only the specific volume is going to change. Effectively, the quality is going to change. Okay, is that fine?
Yes, sir.
Yes, sir.
All right. So let's go to the second part of the question. So the second question says part B. So we have to determine where the point is for 120 degrees Celsius and a specific volume of 0.5 meter cube per kg. Okay, so this is the question. Again, let us see how we would do it had we been given only the plots. If we had been given only the plots, how would we go about doing this? You should be able to first understand how to do it without any calculator, anything. Just figure out where the point is going to be, at least in logic. So we again have, suppose we start with the, we can start with the PV diagram or TV, because we've been given the temperature, we can start with the TV diagram. All right. So in the TV diagram, then let me draw an isobar. So suppose this is the isobar. This is the isobar, and so this pressure will be the pressure, saturation pressure at 120 degrees Celsius. This is the same isotherm because this point is 120 degrees Celsius. Now we don't know where this particular point lies. So what should we do? How do we go about it? We don't know where this particular point lies. So what should be the logic? Anyone? Anyone can answer.
So first of all, we should find T set
T
for
sat is
120.
no T sat for 120 is 120. Did you mean T sat or P sat?
Like for
This
P set, what
uh,
will be the temperature?
So for this, I guess we can initially find V inside at x equal to 0.
yeah. So
And
again,
based on that, if that volume 0.5 is greater than that V inside, then it is inside the dome, or else it is
yeah.
behind
Okay,
the dome.
correct. So we have been given the temperature. Okay, we know what the temperature is. We know what the volume is. So we know that these two will specify uniquely a point in this plane. This P set is just like a red herring. You don't really need to know this, but I have just drawn the isotherm. You don't need to do anything with pressure. You will simply query that at 120 degrees Celsius, when I am in the saturated dome, Okay, this is the saturation dome. Inside this, all the points are in saturation. So I will find out the specific volume of liquid at this point. I will find out the specific volume for t equal to 120, x equal to 0, and I will find out the specific volume at this point, that is V at t equal to 120 and x equal to 1. If I see that, so let me call this Vf and let me call this Vg. If I see that 0.5 is less than Vg is greater than Vf, I can conclude that at 120 degrees Celsius, which is going to be this horizontal line, the volume point is somewhere in between, and so it will lie somewhere in the saturation dome. Okay, if I were to see that Vf is obviously less than Vg is also less than 0.5, then what can I conclude? I will conclude that the volume under consideration is to the right of this point and it is somewhere in the superheated vapor zone. It will be somewhere over here. Or alternatively, if I see that 0.5 is less than Vf, which is obviously less than Vg, then the point will be somewhere over here. But look, this is 0.5. We know that this intuition you should also have. You know that all the points on this curve will have a V something like 10 to the power minus 3 meter cube per kg. Why is that? Why is this true?
Density
pure
of
liquid.
water.
Yeah,
Pure
it will be
liquid.
subcooled liquid. It will be subcooled liquid, and so you expect the value to be this, but you don't really know what, I mean, what values this should be. But these are something like 0.8. These values are something like 0.8 or 0.6 or even close to something close to 1. Okay. So if these values are something close to 1, if these values are something 10 to the power minus 3, then obviously 0.5 will lie in between. This is what your expectation is going to be. Am I right?
Yes, sir, and it also depends upon the temperature, right?
But the order of magnitude will be this. So we expect that the point will lie somewhere in between. So let us do it. Let us see how to do it. Let me just grab hold of everything over here. Just reduce it in size. I hope this font size is still visible to all of you.
Yes, sir, it's clear.
So now let us see. So first things first, we must find out Vf, which is going to be volume of water at t equal to 120, x equal to 0. We will also seek to find the volume water t equal to 120, x equal to 1. So this will be specific volume of saturated vapor. This will be specific volume of saturated liquid. So let's see what they are. First, let us do it using computer. So because the demo version does not let me save, what you should do is open Notepad, write the codes here, save the Notepad files for future reference. Okay, you can always write the program over here, copy paste it inside this, run the program. Once you know it runs, you can save this Notepad file. I will show you how I would do it. So I would say Vf is equal to volume of water. I mean, you could write water, you could write steam, doesn't make any difference. So T equal to 120, X equal to 0. Then Vg will be volume of steam T equal to 120, X equal to 1. Alright. So first let us just query these 2 points. So I've pasted it, I will run it. So I get 0.00106, 0.8913. Very good. So Vf is 0.00106, 0.00106, and Vg is 0.8913. Meaning that this point is 0.00106 and this point is 0.8913. And obviously 0.5 is somewhere over here. This is 0.5. So the state obviously lies in between. Okay. So we've done it. We've found out the point. But now, so what do we know? That this state point is 120 degrees Celsius and V equal to 0.5. Let us alternatively specify this point with the help of quality. So if someone asks, what is the quality at that point? What is the quality at this point? So let us do that. So let me go over here. I will simply say X for the point is equal to quality steam T equal to 120 and V equal to 0.5. So the quality comes out to be 0.5604. Okay. Do you comprehend what has just happened over here?
Yes, sir.
Basically, this point has a quality of 0.56. And can we also specify the pressure at that point? What is the pressure at this point? Obviously, we can. Actually, to specify the pressure, we don't need any other information. So what I can do is simply the pressure at this point is going to be the pressure steam T equal to 120. I can now do many things. I can simply say V equal to 0.5. This will give me the pressure. So the pressure is 198.7. I have queried for temperature and volume. I can equally say, okay, instead of volume, I will just pass the specific or the quality X equal to XP. Let me run it. Again, 198.7. No surprises over there. In fact, I can specify X equal to 0 and I will still get the same answer, 198.7. As a matter of fact, I can specify X equal to 1 and still get the same answer, 198.7. Is it clear why? I mean, I'm telling you this time and again, why this is happening should be clear. If it is not clear, you let me know. I will again explain it. No problem.
Yes, sir. Please explain once more.
So here, if we
Yeah.
choose a volume less than Vf, then we'll get some different pressure.
Yes, it will be a different pressure. You're correct. That's what we did in the first part. Okay. So let me tell again what the deal is. Who asked the question? Let me just read one-on-one with him. Who was there?
Sir, I am Bhanu Pratap, sir.
Bhanu Pratap. So Bhanu Pratap, look, in the TV plane, in the TV diagram, what is the isobar going to look like? This is the isobar. This much is clear to you?
Yes, sir.
Very good. So when the isobar becomes flat, when the isobar has become flat, inside this saturated dome, a flat isobar also coincides with a horizontal line, and the horizontal line corresponds to an isotherm as well. This much you accept with me? this flat line is also now the isobar, and it is also the isotherm
Yes, sir.
because T is on the y-axis. So this entire line is an isotherm, but the isobar also becomes flat. So on this curve, which is inside the dome, the P and T are constant. They are known, and they are not independent. Because once I've specified the temperature and I say that I am inside saturation, this pressure will be fixed. Outside the dome, pressure and temperature can vary independently. Inside the dome, pressure and temperature cannot vary independently. But so inside the dome, what is varying independently? The quality or the specific volume is varying independently.
Okay, sir.
So over here, we have zero quality. Over here, we have one quality. But regardless of being zero quality or one quality, they will have the same pressure and temperature inside the saturated liquid dome. Inside the saturated dome.
Okay, sir. So our main motive will be to find that quality.
Yeah,
Where
either
volume.
quality or specific volume. But we cannot use pressure and temperature. We must use pressure or temperature inside the saturated dome. Outside the dome, we can use pressure and temperature as two independent properties. But inside the dome, pressure does not vary independently of temperature. Pressure and temperature are linked. And that is reflected by the fact that in the tables, in the saturated water tables, there is exactly one-to-one mapping between temperature and pressure. They are not independent. See, if they were to be independent, I could not accommodate that data in a single plot because for a given temperature, I could have any pressure. But no, given a temperature under saturation, I can only have a certain pressure. Bhanu, is that clear?
Yes, sir. Clear.
All right, all right. And that is exactly what I was showing with the help of EES, nothing else. How much time do we have? Only 10 minutes. Let's see. I mean, we must do as many problems as possible, otherwise, it will never be clear. All right, let's do this problem. Oh, we did not do this problem with the help of the tables. So let's do it. Let's do the problem with the help of tables also. So let's see. So at 120 degrees Celsius, we must know, we must still do this. See, once the logic is clear, how we go about doing it is a different question. We must know what the specific volume of saturated liquid is at 120 degrees Celsius. Let's see. Let's see. So we must go to the saturated data at 120 degrees Celsius. So we have saturated water data at 120 degrees Celsius. So at 120 degrees Celsius, oh, this is the enthalpy data. So I must go to the specific volume data. So at 120 degrees, okay, someone has marked it also. So whoever scanned this has also marked. Anyway, so at 120 degrees Celsius, the saturated liquid is 0.00. So let me just take a screenshot of this. So this is temperature, this is pressure, this is VF, this is VFG, and this is VG. So we are bothered with 120 degrees Celsius. So we want to know the point where T is 120 degrees Celsius and the specific volume is 0.5 meters meter cube per kg. All right. So at 120 degrees Celsius, Vf, so corresponding to this, Vf equal to 0.00106 and Vg is 0.89186. Okay, so what did we have from the computer? It was 00106, which is the same, and 8913, we have 89186. Slight difference in the third decimal, in the fourth decimal. Okay, no problem. So now we know that because the V under consideration is 0.5, it is obviously less than Vg and obviously larger than Vf. So we must always look at the schematic. The schematic has nothing to do whether you use a table, whether you use a plot, whether you use a computer, whether you use a quantum computer, it doesn't matter. This mind game will always be there. I mean, mind game, not in the literal sense. So we know that this point is 0.0016, this point is 0.8913, and 0.5 is somewhere in between. So we know that the point lies somewhere in between. Now the question is, what is the quality? We have already figured out the quality from the help of a computer, but no, we will not do it that way. Someone says, no, I don't have a computer. I just need to know the quality with this table. So what should I do? I will
So we
use
use
this formula, which we had derived, right? So this will be 0.5 is equal to, so what is Vf? 0.00106 plus x times Vfg, and Vfg is equal to 0.89080. So x is equal to 0.5 minus 0.00106 divided by 0.89080. I have a calculator handy with me. So what is it? 0.5 minus 0.00106 equal to 0.89080. So it comes out to be, this x comes out to be 0.56010. And this checks out. You see? It checks out. So we have done it both with the help of a computer and with the help of tables. But yeah, so given the temperature, this 120 degrees Celsius, this pressure is automatically fixed. Meaning for vapor, a saturated liquid, saturated vapor, or anything in between, these two are the common points. So I can specify either the temperature or the pressure, but I cannot specify both. I cannot say that I am inside the saturation dome, I am at 120 degrees Celsius and I am at at some pressure equal to 300 kilopascal. I cannot say this because inside the saturated dome, once the moment I specify temperature, pressure is automatically specified. Or conversely, once I specify the pressure, temperature is automatically specified. They cannot vary independently. Inside the dome, you can only use temperature or pressure. You cannot use both.
So the tables that we were using are only for like whatever is inside the dome.
Yes, they are only. So I will go to that table. I know your doubt. You want to know whether there are some superheated steam tables and some subcooled liquid tables, right? This is what you're thinking
Yes, sir.
in the
Yes, sir.
beginning of the class. Come on, you just need to turn some pages. Let's do that. So this is superheated vapor. These are the entries for superheated vapor. And look, because pressure and temperature are now independent, I will have a certain pressure and a certain temperature. Certain pressure and some temperature. We will go into this table later. Okay, so you have entries for different pressures and all the temperatures. That is why you need two sets of variables for this. Pressure and temperature both are varying, you see. this sat, whatever this sat is, that is, what do you think this will be? At 10 kilopascal, the first entry in superheated vapor is sat. I mean, actually for everything there is going to be a sat. It means that that is just the point coinciding with the saturated dome end point. The rightmost point of the saturated dome is going to coincide with this. Fine.
Yes, sir.
So don't believe me. So let's see. So at 10 kilopascal, at temperature equal to saturation temperature. So he doesn't bother to tell you what the saturation temperature is. No problem. At P equal to 10 kilopascal, at just the saturation point, the specific volume is 14.67. Okay, so remember this: 10 kilopascal saturation, 14.67. Let's see. 10 kilopascal, 10 kilopascal. Saturated water pressure into 10 kilopascal, 14.67355. You see?
Yes, sir.
So that is like the last entry of the saturated dome is like the first entry of the superheated vapor. And now you must be thinking, wait, if the superheated vapor, where's the subcooled liquid? Of course, there will be subcooled liquid as well. So these are still the superheated water vapor tables, superheated water vapor tables, compressed liquid water. So these are the subcooled liquid tables. Okay, these are the subcooled liquid tables.
From this table, sir, we can find out VF like similar in the
Yes,
similar fashion.
yes. So VF not on the dome, for points to the left of the dome. Meaning these tables are for these points. These are all the subcooled liquid points. That data table is for this. This entire thing is saturated superheated vapor. And the all the points inside are the saturated steam or saturated water tables, and these tables have two kinds of entries. One is temperature stepping, temperature entries, and one is pressure entries, where the pressure is increased by 5 kilopascal or 50 kilopascal, whatever it is. Look, whatever I've shown you, don't think you can just watch me do it and get away with it. I will tell you what happens the moment you need to do a single calculation. It's like a pin swinging Yorker. You will be caught out. You will be plumb leg before wicket, if not clean bowled. So you must do it. You must sit down, spend some time. It is obviously much easier to do on a computer. It might be obvious by now that if you use a computer, life is very easy. But some people are averse to that, and I respect your decision. No problem. You can use the actual tables, but the moment you have some weird numbers coming in, you need to do a lot of interpolation, and that will be there. I will do it for some problems. Once we get past that, once we stop treating this table as something very sacrosanct, we can then simply use the computer to fetch the values, because then you will see that it takes more time to just fetch the values, interpolate the values. It takes more time to do that than actually solving the problem itself.
So
Comprende? Yeah,
you are talking about the values which are not present in the tables, no?
exactly. I'm talking about precisely those values. So suppose
So
someone says, for example, just as an example, someone says, oh, oops, one way too far. What is this? This is ideal gas. We don't need ideal gas. Just as an example, someone says, okay, give me the property of saturated water at 47 degrees Celsius at some quality. So first I have 45 degrees Celsius, 50 degrees Celsius, then I will have to use the property to fetch some intermediate value. Then, so one interpolation, or suppose I want the specific volume at 47 degrees Celsius. So I will calculate the specific volume at the quality at 45 degrees Celsius. So I will use Vf plus X VFG. Then I will do it at 50 degrees Celsius, another interpolation. Then 47 degrees Celsius. So I will do another interpolation to go between these two values and find out the 47 degrees Celsius. You understand what I mean, right?
Yes, sir.
But this is just like one small step of the entire problem. So you need to keep doing this over and over again. And that is, so more calculations, you're becoming more prone to mistakes, silly mistakes. Those will not be conceptual mistakes. But yeah, mistake is a mistake. Silly mistake or not, you get no credit for it. That's the reality of life. I mean, you, not as in you per se, but as a student, as a person designing something. That's what I meant. All right, guys. So I'm gonna switch off record. Otherwise, the recording will keep going.